online cosmology seminar. So this week, it's our great pleasure to welcome Melis Irfan from the Cosmos group in Saclay. And she's going to present about the importance of being earnest about your foregrounds.
Brilliant. Great. Thanks very much. Yeah, so I'm Mel, and what I wanted to talk about was essentially sort of this central theme that's been following my research in the postdoc that I have. So I'm currently a postdoc at the CEA, but I'm about to finish that postdoc and start a new one in around September, October, and there'll be very similar themes. And even when I did my PhD, it was the same reoccurring theme, which was essentially foregrounds. There we go. So what I want to be talking about, so when I first started my career, I was very much doing, CMB style. I was doing CMB cosmology, so the frequencies I was looking at were around gigahertz levels. Now I'm moving into, so for the latter half of my postdoc and for the next one coming, I'll be moving into intensity mapping experiments, specifically 21 intensity mapping. So we're looking at megahertz frequency ranges, but there are a lot of common foregrounds to both these frequency ranges. And what I essentially wanted to do here was to give an overview of the galactic and extragalactic foregrounds you'll be dealing with if you wanted to do any CMB cosmology or intensity mapping cosmology. So the plot that I'm showing at the top, it's just a little rough hand sketch. It's just to show you the frequency ranges. The intensity mapping is grouped into 3 different kinds of experiment, and we'll be going over that in a couple of slides' time. So this talk is going to contain a lot of ISM physics, and I understand that if you're a cosmologist, maybe you're not fascinated by the comings and goings of a tiny magnetically aligned grain of dust somewhere in the Perseus molecular cloud. But if you are, or if you are ever going to try and get work cosmology from an actual radio receiver, from an actual experiment, you want to do some observational cosmology, then let's say it's a good idea to know your enemy. So that's going to be the bulk of the talk. And then right at the end, we're going to take a few minutes to just discuss what you can do about this. So what kind of component separations are available to you? What sort of branches of methods vaguely can you use in order to get to your cosmology? But before I get to the foregrounds, which is really the bulk of the talk, we should probably discuss the cosmological signals by themselves. So just a recap, so we all know what we're talking about. The cosmic microwave background, so the oldest form of radiation in our universe that we can measure. People have been studying it. So the first measurement from the 60s, we've had satellites going up since about the 80s. It's got an incredibly well-known average temperature, this monopole. When you make more and more precise measurements of it, you notice that there are deviations from this monopole temperature. So those are the spatial deviations that I'm showing up there. And when you look by eye, it's quite Gaussian-like. But when you use more sophisticated tools like the angular power spectrum to probe these deviations, we've actually got a lot of cosmology out from it. So the unique things about the CMB is it's very Gaussian-like spatially, and it's spectrally constant for us. So we're at redshift 0. So the CMB is sitting at redshift 1100. We have no choice but to measure it from Earth or from a satellite above Earth. It's going to be it's a black body radiation. It's going to be a constant temperature for us. And we have satellites like WMAP and Planck, which have been measuring across the gigahertz frequency ranges. The CMB is also polarized. So the CMB has 2 kinds of polarizations. There's E modes, and there's also B mode polarizations. So E mode polarizations come from scalar perturbations at the beginning of the universe, whereas B mode polarizations come from tensor perturbations. So things like primordial gravitational waves. Detecting B modes has been called the smoking gun of the inflationary period. So a lot of CMB cosmologists are very interested in detecting B modes for the first time. And I thought this would be the appropriate time to flash up some upcoming experiments. So these are the ones that have been approved that I know of that should be going ahead. So we have Lightbird over there on the left, and then we move to Pico. These are 2 satellite experiments. They've got launch dates in the next sort of 10 years. And then you have the Simons Observatory, which is on the site of the Simons Array. So this is in Chile. So these guys are all trying to detect CMB B modes. You might be thinking, why the need for the new instrumentation? Because we've already had Planck, we've already had WMAP, we've had a lot of people making measurements. And that's essentially what I'm showing with this plot here. So you can see with this plot, you have loads of measurements that have been made. This is an angular power spectrum, and these are upper limits. We haven't managed to detect B modes yet. All of these plots in triangles are upper limits. Your B mode signal of interest is the black dotted line there at the bottom. So E modes can occasionally get lensed so that they appear to be B modes. That is generally not the signal you're interested in. So the black solid line is not what you're interested in measuring. You can do physics with it. You can learn about gravitational lensing, but generally what I'm saying we're after is the black dotted line down there. And all this graph is showing you is that we've yet to get down to the level of sensitivity where we think these B modes might be found. So it's very much a problem of instrumental noise, as much as it is foregrounds. So we've had to have new equipment. And what this plot is showing here is that, so the purple point, which perfectly detects the B modes at high angular scales, that's a forecast. That's what Lightbird is saying that they might be able to do. They're aiming to do, essentially. It's what they're saying that they're aiming to do. So that's the need for new experimentation. So the next cosmological signal of interest, so to speak, that's going to be obscured by these foregrounds, is I'm going to talk about the technique first before I talk about the signal, because it's quite a broad range of signals actually, but the technique is called intensity mapping. So with CMB, we've been talking about continuum emission over a broad range of wavelengths, but with intensity mapping, it is spectral line emission. So it's something that's emitted at a very particular frequency. So this happens with several lines. So several sort of atoms and molecules undergo these electron spin transitions. A famous one is the 21 centimeter spin flip transition. So if you have neutral hydrogen lying around the universe, you're going to be able to measure radiation from it because of the spin flip transition, and that will be at 21 centimeters. So the idea of intensity mapping is, instead of looking at these specific emission sources, take a broad view of the universe around us. You take a big beam and you measure the integrated emission. So it's integrated over that beam site. And the cool thing about this is that, yes, it's spectral line emission, so you should be seeing it at 21 centimeter wavelength, but the emission, the source of emission will change depending on its redshift. So what you're actually getting is a 3D picture of the universe. So you have the two-dimensional angular information, but then also as the redshift, as the universe evolves, we have a measurement in redshift as well. So we have a 3D picture, and this redshift will mean that you will do the measurement at a whole range of frequencies. So 21 centimeters, which is 1.42 gigahertz. You can also do it at 1 gigahertz. You can also do it at 800 megahertz, and you will be measuring the 21 centimeter signal, giving you a 3D picture. What's unique about this cosmology? So again, I'm harping on about what makes these signals unique, because that's what you use when you're interested in separating it out from its foregrounds. So the signal is Gaussian-like. It's not spectrally constant, as you can see in that figure there. It's changing as there's structure formation, but it's stochastic. So it's not smoothly varying according to some model or some pattern. It's very noisy. There's a lot of information in there. So that's a unique thing. If you are particularly interested in all the different kinds of intensity mapping experiment that are going on, this paper here, the one that I've taken this table from, Kovetz et al., the 2017 paper, is a review of intensity mapping experiments that are currently going on, currently either observing or about to enter their observational phases. What I wanted to show here was the frequency range, because I'll be talking about foregrounds, but I wanted to show that you have a whole bunch of experiments, different lines that they're targeting, the areas of the redshift ranges they'll be able to probe. This is the frequency range they're looking at. It is very similar. All the gigahertz ones, they're very similar to what the CMB cosmologists used to probe. The additional frequency ranges come from 21 centimeter intensity mapping experiments, so that's megahertz. Now, the view from our galaxy is a crowded one. You are going to be doing your observations through a lot of sources of diffuse, like the North Polar Spur there, and compact sources of emissions. This is what I'm calling foreground. So basically a foreground is any signal that is standing between you and your cosmological signal of interest. And that's what we're going to be talking about today. This is a standard picture of diffuse foreground. So there are two kinds of foregrounds. You have diffuse galactic emissions, and you have stuff that's extragalactic and more compact or point-like. This picture I nicked actually off the CBAS guys, so you've got their website site down there, so that that's an experiment that's going on that we're going to talk about in a little bit. So what they're showing you here is how these different emissions change over frequency. So you'll see there'll be some frequency ranges where you don't have to worry about some kind of foreground, and other frequency ranges where you have to worry about most of them, and some frequency ranges where only one dominates. So I have taken this plot and I've graffitied over it with my arrows. So the green arrow, the purple arrow, the yellow arrow. Don't worry about the y-axis when it comes to my arrows. All I want to show here is the frequency ranges again. Those pink and purple bands, they're where WMAP and Planck, these are CMB experiments where they did their observations. These arrows that I've drawn in are arbitrary heights. They're trying to tell you where you've got intensity mapping experiments going on. So we're looking through a bulk of very similar foregrounds. So first I'm going to start talking about the diffuse emissions. I want to start with synchrotron first. What I'm going to do is I'm going to put a stamp in the top right-hand corner. And that stamp is essentially meant to mean if you're doing this kind of cosmology, then this should be of interest to you. So I put a stamp on saying if you're doing a 21 centimeter experiment, if you're doing a CEA intensity mapping experiment, synchrotron emission is a foreground that's of interest to you. When it comes to the CMB, I'm going to assume that the CMB cosmologists are done with intensity-based experiments. They're done with looking at the CMB in intensity. What they're really interested in is B modes. So whether that's true or not, that's the line I'm taking here, and therefore you won't see me talking about the CMB when I'm talking about the foregrounds in terms of intensity. You'll only see me talking about the CMB when we're doing polarization. So for diffuse synchrotron emission, this is a huge deal if you're doing 21 centimeter experiments. It's around 4 orders larger than your cosmological signal of interest. So this is something that it's your largest foreground. So synchrotron emission is caused by relativistic charged particles, so stuff like electrons, stuff like protons from supernova remnants, from cosmic rays. So your charged particles propagating through the galaxy, following the magnetic field lines. This is a non-thermal kind of emission. Now, the energy distribution of these charged particles is very well modeled as a power law, and therefore we can model synchrotron emission quite well as a power law. So that's what you have down there, and you see that we've got a power law with a spectral index. Now, the synchrotron spectral index itself is quite interesting because as these charged particles propagate, they suffer energy losses. And that means that the spectral index changes depending on where exactly you're looking. So what I'm showing on the left is a plot taken from a Planck paper, but it was done by the Gal-Prop group. This is a theoretical, this is their simulations showing how the spectral index for synchrotron emission will change not only over frequency, but the different colors there represent different galactic latitudes. So you can see it changes with position and it also changes with frequency. Now, normally when people talk about synchrotron emission, they talk about whether it's steep or whether it's flat, or they'll say there's a steepening of the spectral index as you go to high frequencies. And that's just what I'm trying to show here on the right. I've just made a little toy plot there where I've taken 2 amplitudes and then one amplitude, and I've scaled it using 2 different power laws. So whether the spectral index is -2.6 or whether it's -3.1, which is, you can see from the left, that's the ranges they sort of stick within. And the more negative you are, the steeper you are, as you can see there. And that's sort of why synchrotron emission is such a big deal for 21 centimeter, so for megahertz frequencies, because it has the steepest spectral index of all our diffuse emissions. So it really blows up at megahertz at frequencies. So that's one for you to consider. Now, most of our understanding about synchrotron emission is tied to this map, the top one there. So that's the Haslam 408 megahertz map. That is an all-sky map that was made of our galaxy centered at 408 megahertz. So you'll see a lot of people will use this to inform their models when they want to do cosmological, they want to do sort of simulations to see if they can extract their cosmological signal from a whole bunch of foregrounds. You'll see the Haslam map popping up time and time again. It's a very, very useful map, but it has its flaws. I mean, it suffered from non-Gaussian noise effects. There's going to be FreeFree in there. I mean, this is a pure map of the galaxy, but we use it as a synchrotron template. what I wanted to bring everyone's attention to, these two experiments down at the bottom there. So on the left, we have CBAS, and on the right, we have SPAS. These are two experiments with the intent of making a full sky map. For CBAS, it's centered at 5 gigahertz. For SPAS, it's centered at 2.3 gigahertz. They're going to make an all sky map in intensity, just like Haslam did, but then they're also going to do it in polarized intensity. So this is going to be, both of these are going to be really big resources to the community when their final surveys are published. And they are more than halfway through. There are results from SPAS already. A lot of them, if you use the Lambda Legacy Archive, there's a lot of, there are maps up there as well. But I haven't seen the full sky in intensity, polarized intensity for either of them yet. But that's going to be very exciting when it comes out. Now, synchrotron is also polarized because you have charged particles in a magnetic field. So now I'm talking about foreground if you're interested in B modes. This is one of the standard plots. This is one of the many plots. There are more updated ones. I think I revert back to the ones that I'm used to. The idea is if you're trying to look for B modes, your foregrounds are huge. So the blue one is dust. We'll get to thermal dust later, but you can see synchrotron emission is polarized and they're looming over your B mode signal. So something you have to consider, what I wanted to show here at the bottom, this is a plot from Vidal et al. This is sort of a warning about leaving the plane and thinking that you might be safe if you've got off the galactic plane. So generally, when you design your experiment and you know you're going to want to measure some cosmology, you generally don't get it to point at the galactic plane. So the idea is you try to point it in a really quiet region of the sky, foreground quiet region of the sky. So what these authors are showing here, this is a WMAP K-band, so it's around 23 gigahertz, polarized intensity map. They have drawn on and identified features. So some of them are old features, some of them are new features, but you get these beautiful spurs and loops in polarized synchrotron emission. And I just wanted to highlight that a lot of these go very far off plane. So putting yourself in what you think is an empty region of the sky might not necessarily be as empty as you think it is. So that's something that I wanted to highlight. Now, if you're doing a 21 centimeter intensity mapping experiment, you might think, yes, well, it's intensity. So I'm going to get away from polarized foregrounds, surely. But you'll be making your measurement using physical equipment. So whatever your hardware is, it's not going to be perfect. So you're going to get leakage. You're going to get leakage probably from your intensity into your polarization, and then you'll also get leakage from your polarized emissions into your intensity. It works both ways. So you have to deal with, you still have to deal with polarized synchrotron emission, even if you're doing an intensity mapping experiment. Now, if the universe were a fair and reasonable place, we would just have the exact same signal essentially as we deal with in intensity. There would just be sort of a certain fraction of it, the polarization fraction. So let's say 30 to 40% of it would also be present in polarized intensity. What happens if you're under 2 gigahertz though, is you actually have this depolarization effect called Faraday rotation. So Faraday rotation is a frequency dependent depolarization effect. So what you have here is the intrinsic angle of polarization angle of your particular emission source that you're looking at. As it travels through the plasma, as it's propagating, it will get rotated due to the physical properties of the plasma. So your rotation measure is dependent on, the temperature, things like physical properties of the plasma around it. So it varies across the sky. What's important with Faraday rotation is it's a frequency dependent depolarization. And this is illustrated really beautifully by the Reich 1.42 gigahertz all sky survey. So they, like Haslam, they made an all sky map. They made it in intensity, and you can see in intensity you have very similar features where you have the galactic plane going through the middle, you have the north polar spur. Then in polarized intensity, you can see the depolarization. You're missing a large amount of the features. You're missing the galactic plane. You're missing a large amount of the galactic plane. So you have to deal with this depolarization. And the trick of it is it's frequency dependent. So if I were to make a map at 1.3 hertz, at 1.1 gigahertz, this depolarization would be different at each of those frequencies. So what Faraday rotation is actually doing is it's breaking the correlation across frequencies of your foreground. It's making it look a bit more stochastic across frequencies. Remember I said that was something that your cosmological signal of interest does. So for 21 centimeter intensity mapping, a lot of the understanding is that the cosmological signal is a little bit stochastic, a little bit noise-like. It's the foregrounds which are very smooth spectrally. And Faraday rotation massively throws a spanner in the works in that respect. Okay, so that's one. That is one emission out of quite a few. So now we have FreeFree emission. So this is an intensity. It's intensity only. It is electron-ion collisions inside of the warm ionized medium. So it's something that comes from areas of hydrogen plasma. Also, what's going on in hydrogen plasma is you end up with H-alpha emission. So actually, we've got quite a nice idea of what FreeFree emission looks like because of this composite H-alpha survey map, which I'm showing there. There you go, that one. So this is a H-alpha map, and what the authors have actually done is they've even given you conversion factors, so you can turn this map into a free emission template at stuff like WMAP and Planck frequencies. So we have a fair idea what it looks like. It can be modeled more parametrically using actual properties of the warm ionized medium, or you can model it as a power law. It also works as a power law. The spectral index of which is much more well behaved than synchrotron. So it's not believed to change over pixels across, spatially. It changes across frequency, but by a very, very small amount. So it's quite a stable emission. It's much more well behaved than synchrotron. What I did want to point out with this slide is that free emission and synchrotron emission are heavily degenerate with each other. So if you're working on a 21 centimeter experiment and you think it might be quite cool to try and pick apart the synchrotron and free emission from each other, be aware that you need a lot of information to do this because there's a lot of degeneracies and you probably don't have the frequency range necessary you might need to bring in a lot of ancillary data because these two things are heavily degenerate between each other. Not a big problem when you're trying to get to your cosmology, but if you were trying to fit out each individual foreground, you'd need to keep that in mind. Okay, so now we're going to go a little bit higher up in frequency, between around 15 and 60 gigahertz. So this is where you would be if you wanted to do a CO intensity mapping experiment. What you get here, as well as having to deal with free and synchrotron emission and intensity, is anomalous microwave emission. Now this one gets the most exciting name because it has the least understood emission mechanism. So it was first discovered as an excess of emission when people were doing some observations in the mid-90s in the North Celestial Pole region. It was discovered as an excess of emission, and still it can be seen quite well as bumps, as an excess of emission. So if you make these SED plots, you can see the little bump of spinning dust where you have to add spinning dust in there to explain what you're actually observing. So spinning dust is one of the strongest explanations for AME, and in most places, what you're looking at is spinning dust. So these are very, very tiny dust grains that are rotating. So they have been used with a lot of success to model this excess of emission that is AME. There's still a lot of queries that hang around AME, which is why I'm calling it AME, and I'm not just saying the other kind of emission is spinning dust emission. I'm going to continue to call it AME because there are specific regions where it doesn't quite seem to be behaving itself. So even when you use spinning dust as a model, so what you can see at the top here, this map from one of the Planck collaboration papers, this is within the Perseus molecular cloud. They've used the spinning dust model to fit the extra emission they've seen. It's worked, but it's peaked at around 15 gigahertz as opposed to 30 gigahertz, which is, it's something. Perhaps it's not a case for massive alarm, but it's a little bit of a deviant. Next, below that, you have another plot where the authors have been observing in the Small Magellanic Cloud, and they found an excess of emission. They put in the spinning dust model to try and explain it, but it wouldn't explain it. So they had to invoke another model that involved tiny dust particles that were magnetic. that worked. That explained what they saw in intensity, but it made a prediction that AME should be a polarized emission then. If it's magnetic spinning dust grains, then you should have a polarized component to this, which has yet to be detected. There's never been a polarized detection of this excess. And then last of all, a couple of years ago, there was a paper in Nature about some guys that were looking inside of protoplanetary disks, and they said it's not PAHs at all, it's not tiny dust grains, it's actually diamonds. It's diamonds that's doing it, which is not so common that it can explain sort of what we're seeing all over the sky, but this was a big and interesting result. What I'm essentially trying to say if you're doing a CO intensity mapping experiment, maybe don't put it in the middle of the Small Magellanic Cloud, not that you would anyway, but it's interesting to keep an eye on these sort of ISM developments, and also it's an extra opportunity. So experiments like CoMapper, what they're doing is they're actually using their cosmology experiment as a way to probe this bit of ISM, which is quite cool. And then all the way up at the highest, the frequencies that I'm going to talk about, so anything up over sort of 60 gigahertz to the Planck HFI maps, essentially, so like 857 gigahertz, you have thermal dust emission. So this is interstellar light, it's absorbed, it's re-emitted by dust grounds. If you wanted to do a C2 intensity mapping experiment, this is one of your foregrounds. You have several foregrounds. This is one of the things you have to worry about. It's had a lot of success in being modeled as a modified black body. So you see the three parameters in there are an opacity, it's black body, so you have the temperature of the dust, and you have a spectral index that scales it across your frequency range. So it's had a fair bit of success as an MBB model. Thermal dust emission is also polarized. So I put that plot back up that I had a little while ago, and you can see that as the plot comes back, there is the massive polarized dust signal looming over, again, your B modes. This has meant that people have started to take more and more interest into the modified black body and whether it's actually good enough to be used to get down to the B mode level. Because we don't know where B modes are. We know that they're very, very faint. We have a certain prediction. They could be much, much fainter than even our prediction. So this is something that's of a lot of concern for CMB cosmologists, and it's something that they're taking into a lot of consideration. So what I thought I'd flash up here are just two interesting prospects. The top one is an experiment, and the idea is to make a three-dimensional map of thermal dust. So the idea is you are treating the dust cloud as if it has one temperature. What if you have several dust clouds in front of each other? What if they have different spectral indices? What if at lower frequency one of them becomes more prominent and has a different temperature to what's more prominent at higher frequencies? Are you going to introduce decorrelations across your frequencies? Not that there has been a definitive sign of this yet. Like I said, there's been a lot of success with the MBB model, but is it good enough? So that's an experiment there. There's also the paper there at the bottom is another method that's it's just a mathematical method that uses Taylor expansion to try and say, okay, there might be deviations from the modified black body model, but maybe we can capture that as well in our parameterization so that it doesn't interfere with our cosmology. So those are interesting prospects for thermal dust as far as CMB modes. Now, you knew this was going to happen. You knew that we wouldn't do a foreground sort of discussion without talking about BICEP 2. So here is the obligatory slide on BICEP 2. So in 2014, BICEP 2 observed B modes. They thought that it might be CMB B modes. It was foreground B modes. So the experiment was observing in a region of the sky that the available models at the time had told them would be incredibly low on foregrounds. So they did their observations, they detected a B mode signal. They cross-correlated this signal, again, with the available models at the time, what they thought thermal dust B modes would look like. They didn't find any correlations. They believed that they had found the primordial B modes, so the CMB B modes. The Planck results came out later that year, or maybe a year later, I think later that year. But when the Planck polarization results came out, it showed that there is still quite a high level of thermal dust. So this is the standard word to the wise about foreground avoidance. At the end, we're going to talk about what are the various things you can do, what are the groups you can do in terms of ways to combat foregrounds. And one of those techniques is avoidance. So this is just a reminder that it's very important to really understand the astrophysics, the models, to be very confident in them if you want to try avoidance. Now, that is actually it for my galactic foregrounds. There are, so when I said to you at the beginning that a foreground is anything that's standing in between you and cosmological signal of interest, I primarily deal with the galactic ones, but it needs to be noted that if your cosmological signal of interest is sitting at, I don't know, redshift 2 or 3, anything that's coming from redshift 1 and 2 is also going to be a foreground for you. So as long as there's been light in the universe, there have been these the extragalactic background light, so the light from these unresolved galaxies. This peaks at the far infrared. It's called the cosmic infrared background. So this is starlight from unresolved galaxies, essentially. It is, for those of you who are particularly eagle-eyed, when I put up where I plot a couple of slides ago talking about C2 foregrounds, I wanted to talk about thermal dust. Thermal dust was by no means one of the biggest ones up there. You also have the cosmic infrared background. It's going to be something that they need to take into account. It can be modeled as a modified black body. It is very Gaussian, like if you're just looking at it by eye. If you wanted to have a shot at making your own CIB maps, what you can do is you can take the Planck HFI data. If you have a good dust template, take away your thermal dust from that, and what you should be left with is the noisy CIB signal. And point sources. So if you can resolve out your other galaxies, they are extragalactic emissions for you. So they are point sources. These split into two groups: flat spectrum and steep spectrum sources. So what I've put up here is I've made a little sky map of point sources so that you can see the contributions that they have to your total observations. This was made using a recipe that's given in Batty et al. So what Batty et al. Does is he essentially the authors, they have a look at point source catalogs, of which there are many, but there are a lot at 1.4 gigahertz. And they use that empirical understanding of point sources to figure out a way to describe the point source contributions at megahertz frequencies. So the recipe is in there if you want to do it. What I'm showing you here, following that recipe, is the point source contributions at 580 megahertz, 40 arcmins, and with a cutoff frequency of S max. So when you hear people say S max or S cutoff, sorry, it's a cutoff flux density. I said frequency, I misspoke. It's a cutoff flux. And the idea is you believe that a source is so bright that it will have been identified by a point source catalog, so you'll be able to find it and remove it. So I'm saying that anything above 1 Jansky has been thrown away here. What I wanted to show is that point sources actually make 3 different contributions to your overall measurement. So you have the actual Poisson or shot-like contributions, which are the point sources, which is fine. For those that you can't particularly fully resolve, you get this clustering effect. And then also, there's an offset temperature. So it's going to provide an offset to your map. So the ones that are completely unresolved, you can see that the average of this map is around 1.8 Kelvin. So those are the contributions that point sources are going to add in there. This is something that I think is quite cool, something that gets flung around a fair bit when something weird happens at megahertz frequency ranges. And I thought it'd be cool to mention it. It would be cool to discuss it. It is the arcade excess. So if you have an absolutely calibrated instrument, you can go after the CMB monopole. You can actually make a measurement of the CMB monopole like Kobe Forrest did. So Arcade 2 was a balloon experiment, and it decided to measure CMB monopole, and it had, I think it was 9 or 10 observational bands, but it spanned from around 3 gigahertz to I think 90. This is a plot from their paper, and you can see they've drawn in a dotted line the CMB monopole. they have their observational points with error bars. So we are considering how close the observational points with error bars are to the monopole temperature. So they found everything in order to 1 or 2 sigma. So I know that some of the points have really big error bars, but everything, you know, sort of within 1 sigma, except at 3 and 8 gigahertz. So they found an excess of temperature at megahertz frequencies, and they actually fit this excess using a power law. So using a minus 2.6 power law, very similar to what you would expect for steep spectrum radio sources. There were several proposals for what this excess could be caused by, but one of the proposals was that there might be an additional population of radio sources that are incredibly faint, but numerous. There's loads of them, and are pushing up the megahertz background temperature. As time goes by, more and more sensitive point source catalogues come out. So there's the quote there is from a paper that I found that had, they were doing point source surveys to a sensitivity of 1 microjansky. And no evidence yet that I'm aware of has been found out about this very, very low intensity but numerous point source population. But there remains this excess. If there is an excess, if the analysis was done correctly, if it's actually true, then there remains this excess. And like I said, every now and again, when something peculiar happens at megahertz frequencies, you might hear people talk about the arcade excess. So it is something interesting to keep in mind. And polarized point sources. There are polarized point sources. This is generally not thought to be a big deal for B mode foregrounds. So what I'm showing here is a plot of these are Planck frequency channels. So 70 gigahertz, 100, 143, and 217 plots taken from this paper here. They're showing you where we expect the B mode signal to be. They've put in what they expect the power contribution to be from point sources, and they've put in so 4 different options. Essentially, you have 2 different cutoff frequencies, and you have 2 different polarization fractions. So it's how much of your point sources that you've seen from intensity based surveys and intensity point source catalogs, how many of them do you believe will be polarized, or what fraction are they polarized? What's your cutoff frequency? How many of these can you just throw out because you've identified them? And unless the B mode signal gets incredibly low, unless it's far lower than what we think it is, so I think this has been almost ruled out. I think the current understanding is around here and lower. So unless it's getting too low or lower than previously expected, these shouldn't be a big issue. If you're doing a intensity mapping experiment, as I said, anything that happens in polarization tends to leak through. There are 1.4 gigahertz polarization surveys available for polarized point source catalogs. There didn't used to be a lot at megahertz frequencies, but ever since the SKA and its precursors started turning on, this is quite an exciting sort of new batch of observations are coming out. So these are the results from like the GLEAM survey. They've just got the region of the sky that they're observing, and they've identified these point sources. I think the lowest one is at 9 millijanskys. They've also managed to, they've also color-coded them in terms of their Faraday rotation. So this is just to say you will have point sources, polarized point sources, they will be Faraday rotated. They will be another problem that you have in 21 centimeter intensity map. So now just for the last, I think it's the last 2 or 3 slides. So I have essentially gone through every single thing that I can think about in terms of foregrounds for cosmological experiments. And the idea is, I think it's a good idea to know what you're getting into, to know what you're going to have to dealing with, so that you can try to choose the best kind of method to get around it. So I think as much knowledge as you have is really what we want to go for here. Now, there are 3 sort of things that you can do two of them count as component separation. So the first one is avoidance. So you're not trying to take a measurement that includes foregrounds and cosmology and then do some sort of separation between the two. What you're trying to do is you're trying to very cleverly plan your experiment so that you don't have to deal with the problem of foregrounds. So you've seen that there you can do your avoidance by sky region. We talked about that before. There's something actually, so I won't talk about that again, but there's something actually a little bit clever you can do if you're using interferometer, which is quite cool. Then your other methods can be grouped into what is essentially blind and what is essentially parametric methods. And we're going to talk a little bit more about that, but a blind method is one where you shouldn't have to know anything about your astrophysics at all. So you can forget a vast amount of detail that I've given you, but you need to know what it is that makes your cosmology unique from your foregrounds. And a parametric method, for a parametric method, you aim to say, okay, look, I've got an observation. I know for a fact there are 5 different kinds of thing in there. I know how to model those 5 different kinds of thing. I want to get out the cosmology, I want to get out the foregrounds, but I want to separate each individual foreground from the other one. So I want to end up with 5 results. So those are parametric methods. Okay, so for foreground avoidance, the last bit on avoidance is a little bit of a cool thing that you can do if you're taking the Fourier transform of your data, which an interferometer will do. So we were talking about how the intensity mapping signal is a 3D one. So I'm using wave numbers now because I'm in Fourier space. So you have, instead of X, Y, and Z, KX, KY, KZ. They're generally grouped together into K parallels. So you have your line of sight modes that represents your redshift information if it's cosmology, or your spectral behavior if it's in terms of your foregrounds, and then you get your angular information. Now, the nature of foregrounds is that generally they are very spectrally smooth. So they can be modeled with very little information. There's not a lot. So for instance, we've seen just power laws will be enough to describe for you the behavior of the synchrotron emission. So they are generally well contained in terms of a very few number of sort of low K parallel modes. But the actual cosmological signal of interest has much more structure, much more stochasticity in there. It takes up an entire range of K parallel modes. So if you know your instrument very, very well, you can do this avoidance technique where you essentially throw away a lot of your Fourier modes until you're left with just a small corner that represents your actual cosmological signal of interest. So you don't need to do anything else other than know your instrument very, very well, which is quite hard. And also, you will be throwing away a lot of the modes available to you. So you will be doing these observations, but you'll have to get rid of a lot of the Fourier modes. So it will reduce the sensitivity of your results, but this is something that is a possibility for you. Now for blind methods, there's always quite a good review of stuff if you're looking through Planck papers. So for Planck, if you look at their CMB results, they famously have four maps. So I think they actually only do the angular power spectra on one of these methods, but they have 4 different methods, and they will go through and show you CMB maps of all these 4 methods and the pros and the cons. The blind methods in there are NILC, SEVM, and SMECA. I think, sorry, that got auto-corrected, that should be 7. So 2 of these methods, SEVM and NILC, they use something that is very unique about the cosmology in order to be able to separate it out from their foreground. So that's what you're aiming to do with the blind method, but they use something that is unique to just the cosmic microwave background, so the fact that it's constant across all frequencies. And they use that to make their separation. NILC actually has been extended or generalized. So you now get this GNILC algorithm. And what you can do with that is you can actually put in a small piece of information about your cosmology. So you can do sort of a PCA style analysis where you take the covariance matrix of your cosmology, you use it to whiten the total covariance matrix, and you take the eigenvectors and you essentially reduce the dimensions that you're looking through to, instead of just being loads of observations, you now have stuff that looks like your cosmology and stuff that's foregrounds, and you can get rid of your foregrounds, leaving you with the things that look like your cosmology. So for GNILC, you can use it for, and it has been used for 21 centimeter experiments. Then you also have sort of ICA methods like SMECA and FASTICA. So the idea is they separate out your total foreground, your total observations into things that are independent from each other. So things that stand out spectrally and are independent from each other. So what you'll end up with, so it's a way of separating out instead of getting the bulk foregrounds and the cosmology, you'll get several different kinds of foregrounds, but these won't necessarily represent physical foregrounds. So things like synchrotron emission and FreeFree emission, because they're so heavily degenerate, they're not going to look like individual sources to an analysis like an ICA style analysis. So what you'll tend to get is actual two different kinds of physical emissions being put together. So stuff like AME and thermal dust, stuff like FreeFree and synchrotron emission will go together. Not a big deal if you're trying to look for your cosmology and you're not interested in your foregrounds, fine. You just want to pull out sources that are independent from each other. A cool little way to go, and something that you can do, is semi-blind methods. So these are kind of cool hybrids. So if you were looking at the latest Planck polarization results, the ones that came out in 2018, you'll see that SMECA, a blind method, was used actually in a semi-blind way, and it has produced foreground maps of thermal dust and synchrotron emission in polarization. And the way they did this was they extended the algorithm so that they extended the algorithm to include information about the foregrounds, so that there were two different foregrounds they were interested in, and that one emission in polarization essentially vanishes at high frequency, and the other one does the inverse. So you have the option available to you to form hybrids, which is quite cool. And then lastly, you can go whole hog. You can do the parametric fit. So what I'm showing you here is a table from one of the Planck papers, and it's the commander method. So this is a parametric method where they are doing a joint fit to the LFI and the HFI data. They're all out just trying to parameterize and fit everything that's present. So you can see they have everything that we've spoken about, and they have quite a few other things in there as well. And at first you might be thinking, why have they done this? Why have they used all of the information available to them? Why didn't they just, for instance, pick like the 20 to 30 gigahertz range, where at least maybe you wouldn't have to deal with something like thermal dust? Because as you've seen, there are some, if you're looking in frequency space, there are some areas where one or two emissions are far more dominant than other ones, and other ones just maybe they can be considered negligible within certain frequency regions. And there exists a bit of a catch-22 in our galaxy, and in that a lot of these foregrounds are so heavily degenerate with each other. So spatially, they have a lot of similarities. You can see galactic planes in all of them. So they have a lot of shared sort of spatial features. Spectrally, things like synchrotron and FreeFree emission, they're very hard to pull apart. So while at first you might be thinking, what if I limit the observational range to try and make sure that there's not so much going on in there? What you actually find is not only will you be wanting to use all the observations that are available to you, you might need to even pull in more data, so ancillary data, because of all these degeneracies. So that is something else you need to consider. So this is now my last slide, and instead of sort of summarizing everything that I've been talking about, because I know it's quite a lot, it's a brain dump, I want to summarize my point and why I gave this talk, why this is something that I wanted to share and discuss. It's essentially, what can you do if you are an observational cosmologist? What are the methods that are available to you? What are the problems that you have around you? If you can use as much information as possible, I think you can come up with the best solution. So this is a flowchart. There's you there getting up to some cosmology, and depending what frequency range you're interested in, you'll see the different kinds of cosmological signal you're after, the different kinds of foregrounds you might interact with, and then again, depending on what kind of instrument you're using, what are your options available to you? Could you try a sort of case-based avoidance technique? Could you try, are you very worried about your instrumental effects? Are you very worried about things like, oh, I don't know, my beam, it's not Gaussian, oh no, I've got loads of polarization leakage? Are there so many other things in there? It's better for you maybe to just go with a blind method. Or are you like, no, I know what's going on. I'd be interested in doing some ISM. I'd like to get the astrophysics out as well. If you would like to try parametric methods, do you have the range of frequencies available to you? Do you have enough information? If you don't have enough information, are there auxiliary maps available to you? Are there other surveys available to you? So this is pretty much it for me. I will leave it up here. So I'm happy for discussions. I'm also happy if there are other kinds of foregrounds or other kinds of effects that I have left out, and I can add them to my big list of worries, which I'm compiling. So thank you very much for your time.
Yeah, thanks a lot. Great talk. Hope everyone enjoyed it. Let me quickly conclude the live stream on YouTube. So for the folks on YouTube, if you want to ask questions, please leave them in the comment section.